start with this series of lectures on advanced quantum field theory. So the official title of the course is something like Explorations in String something. But what we will do is actually advanced quantum field theory. So that's the real title of these lectures. What we will be doing is exploring some advanced topics in quantum field theory. We will discuss conformal field theories, for example, which are a particular class of quantum field theories, which are, if you want, the most fundamental quantum field theories that play a very, very special role in quantum field theories. We will also explore ADS-CFT, which tells us that some quantum field theories can be described by string theories. So there is such thing as something called the ADS-CFT duality that tells you that there are dual descriptions of gauge theories as string theories and string theories as gauge theories. This is something very, very powerful, both technically and conceptual. For example, it provides, if you want, the cleanest non-perturbative definition of what we mean by quantum gravity. What is the definition of a unitary theory of quantum gravity? And as we will see, the best way to define quantum gravity in a precise, unitary, totally quantum way is by defining it by being the dual of a theory that we understand very well, which is a quantum field theory. More than that, it's a very special quantum field theory, simpler than usual quantum field theories, known as a conformal field theory. So if you want, these are topics within quantum field theory that have connections with string theory, with many other ideas in physics, statistical mechanics, conformal field theory, and so on. And if you want, so this would be the main title of what we are going to cover, but a subtitle would be maybe fair to say that it will be mostly about ADS, CFT, and some related ideas. So last year I gave already this course. I've been giving it already for a few years. And normally I try to do it very different from year to year, in particular because the lectures are online. So if you want to learn more, you can then watch the other lectures of the other years. So it's a good way so that the amount of information in PIRSA is increasing monotonically. And if you want, you can always learn more stuff by just watching the same lectures I gave. And of course, there will be a big overlap, but there will be many new things that I'm trying to cover this year that I did not cover the previous years, and vice versa. What else do I want to say? Yes, I want to say that another reason why this year we will do it in a bit different than previous years, that this year you did not have a lecture course on conformal field theory. So in the previous year there was a course like John May gave on conformal field theory, which was actually a very useful course, but unfortunately you did not have it this year. So maybe 1/3 or even a bit more than that will be devoted to the study of conformal field theories. Okay, so this will be where we will start. So the plan is to start from conformal field theory, then go to ADS-CFT, which is a duality between a theory of quantum gravity and the conformal field theory, and then consider some applications of this duality where we revisit some of the ideas that we have seen in a more general treatment of conformal field theories, together with some modern tools in holography. Very good. So today we will start with some general motivation for studying conformal field theory. So today it will be mostly blah blah. There will be not too many serious formulas. It's more like a philosophy course. Very good. So conformal field theory. So conformal field theories. Let's see if I can still write sentences. Conformal field theories are quantum field theories. Okay. Now, quantum field theories, they are particularly hard and particularly interesting because they have many scales, right? You have a conformal field theory, and physics at different scales, they can be totally different, even the degrees of freedom that you use to describe. At very high energy, we have quarks and gluons and so on. That's totally the wrong description at very long energies, where we have blue balls and hadrons and so on. So quantum field theories are very rich and very intricate and very non-universal because there is an abundance, abundance of different scales and correspondingly different physics at different scales. So depending at what kind of energy scale you are studying, your quantum field theory will exhibit kind of a different behavior. That's what makes it very hard, kind of not universal. There are many quantum field theories, and the behavior at different scales will be different. However, there is this notion that as you zoom in a lot or as you zoom out a lot, as we will explain in a bit more detail soon, some universality appears. And you get conformal field theories, which are theories which have more symmetry than usual quantum field theories. So therefore, they are simpler. And in particular, they have scale invariance. There is no scale. Okay? So this is a major simplification. It's a major simplification if we can study quantum field theories, which are, of course, the building blocks of nature. But if we can simplify them somehow and have some object which we are somehow capable of treating, that's a big improvement. And these conformal field theories that have no scale are a very good example of theories where we can make progress and where we can understand things. So of course, because conformal field theories have no scale, they describe massless particles or massless modes, right? So this is a theory which is relevant when we have massless excitations. Right? So if we have some massive particles, a mass of a particle sets a length scale. So of course, these are the kind of theories that are, if they are invariant under scale, by definition, they are theories of massless modes. In statistical field theory language, what is a mass when you have some spin system or some system of some statistical field theory system? What is a mass? A mass is what governs correlations, right? So if you have masses, if your fields are massive, it means that your correlation functions decay exponential, and the mass tells you what's the correlation length with which they decay, right? This you have seen with John, right? When we studied correlation functions, we saw that away from a critical point in a statistical field theory problem, correlation functions decay exponential, except if you are exactly at a critical point where they decay as power laws. So conformal field theories arise when, in statistical physics, or in condensed matter, in statistical physics, conformal field theories arise when the correlation length goes to infinity, where you do not have a typical scale, a typical correlation length. Okay? Okay, very good. So when do we expect CFTs, or how do we expect CFTs to emerge from quantum field theories? As I'm claiming, they are somehow very nature. For example, suppose we consider the ultraviolet limit of a quantum field theory. So let's suppose that we are at high energies, at very high energies. Okay? If we are at very high energies, it means that our energies, if our energies are much bigger than the masses of our fundamental excitations, then in practice, it is as if they were massless, right? So the mass, their mass becomes irrelevant compared to our energy scales, right? We are pumping so much energy into our system that everything is relativistic. And we do not see, the particles are effectively massless. So the mass measured with respect to our energy that we are probing is effectively zero. Okay? So particles are effectively massless. And then we have a CFT in the ultraviolet limit. Ultraviolet means high energies, or equivalently, short distances. Right? We know it's equivalent. Of a quantum field theory. So if we have a quantum field theory and we zoom in a lot to short distances, or we consider very high energies, then compared to those very high energies, the particles are effectively massless. So we obtain a theory that has no scale. Is it clear? In other words, we consider some energy that is much bigger than all the scales of our theory, such that we wash them out. Now, at very low energies, the same thing. So at low energies, massless massive modes are irrelevant because they are massive, so they are not excited. They cost some energy to excite, and we are at very low energies. So the massive modes are not important to describe the low energy dynamics. So only massless modes are relevant. So again, we conclude the same thing, that we have a conformal field theory in the infrared, that is low energy or large distances, of our quantum field theory. Okay? So the picture is that we have a quantum field theory. There is some ultraviolet fixed point. As we zoom out, that is, as we move under the renormalization group, we go to another theory in the infrared. This would be what we call the RG flow. And we have a CFT in the UV, and we have a CFT in the IR. This is the typical picture that we have describing quantum field theory. So if you want, studying quantum field theories is the study of the RG flow between two conformal field theories. So all quantum field theories, they are like anchored between two CFTs. There is one CFT in the IR, one CFT in the infrared. And the hard part of the CFT is, of course, studying the different, what happens at intermediate scales, where there could be crossovers, different behavior. And at the very high energies, or at very low energies, you have a CFT description, where you have no scale, and where things simplify drastically. Now, sometimes to get a CFT, you start in the UV, you flow to the infrared, and unless you tune carefully where you start in the UV, you get something boring in the infrared. Okay? What do I mean by this? For example, when we have a magnet, we have some UV description in terms of some spins that interact. Unless we tune carefully the temperature, as we zoom out, we will get to something boring, like O spins up or O spins down or something uninteresting. And we will get to something interesting, some interesting CFT, only if we tune some parameter. So I gave you some page, for example, which is from some critical phenomena book. I think probably John already described these pictures to you. So in these pictures, do you all have this picture? So we see some, what do we see here? Let me just describe by words this picture. So we start from a picture where everything is black. This is when you start with some temperature, which is below the critical temperature. Then we start to have some white regions, and then here in this right middle one, we have white regions of any possible size. And then as we increase more the temperature, then we go to this white-black dots without, where the white regions are again very small. So if we look at these pictures, if we ask, what is the typical size of a white region? Well, in the first picture, it's very small, right? The white regions are very small. In the last picture also, there's only very small white and black regions. In the middle one, it's the one where you have white regions of any possible size. You have a very big one to the right, you have a small one in the middle, you have regions of all possible sizes. If you would zoom in and out on this picture, you would not find the difference. So just by looking at this picture, I cannot tell you at which scale I am. I cannot put a scale and say, this is 1 nanometer, this is 1 centimeter, this is 1 meter. I don't know. Because it's invariant on the scale. I change the scale, I zoom in and out of this picture, and the picture would always look the same. This is what a theory of scale invariance is. On the other hand, this is not true. If I zoom out here, it will become totally black. Right? For you, this is probably totally black. For me, I see some white. So we can tell what's the scale. We can say what is 1 centimeter, so there is a scale here. There is a scale here as well. If you zoom it out, you will see it as gray. If you zoom from close, you see there's white and black, but not in the middle one. So sometimes what happens is you always have a CFT, but sometimes it can be a boring CFT, an empty CFT with no fields or something like this. And sometimes you have an interesting CFT if you tune carefully. Changing a bit the temperatures means starting from a slightly different point, and then you go to some boring CFT. Or to some slightly lower temperature, and you go to some boring CFT. And unless you start exactly with the right temperature, you flow to the good one, where you have some interesting critical phenomena. Okay? How many things do we have to tune in the laboratory to go to the good, to a good critical point? Just the temperature. Okay? Just the temperature. If we tune the temperature, we can get these nice pictures. So there is one relevant operator in the theory. By the way, we will see that later. But okay, what I want to say in these pictures is that just let's put some captions on these pictures. So if we consider the correlation length that depends only on the distance between two spins, so let this R be, there is some I minus J, let this be the distance between points I and J, and let this be the correlation function between Si Sj minus Si Sj. Si and Sj are spin variables. They can be quantum or classical, doesn't matter much for this discussion. Then what will happen is that this will behave as e to the minus the distance over some correlation function if the temperature is not at the critical temperature. And this will behave as 1 over the distance to some dimension, in this case of a spin operator, delta spin, when T is at the critical temperature. And what happens is that the correlation length diverges as T approaches the critical temperature. More precisely, there are typically power law behavior, T over Tc, minus nu as T is approaching the critical temperature. So there is this critical phenomena. You approach the critical temperature, your correlation lengths become larger and larger, you get scale invariance, and your correlation functions are no longer exponential. And if they are exponential, of course, you can detect what's the length scale. But they are not exponential, so they are power-like, and therefore you cannot, just by looking at the picture, tell at which scale you are. You have no scale. Is it clear? Am I going too fast or too slow? Is it clear? Yes.
So may I say that CFT is the QFT in the critical point?
A CFT appears when you consider quantum field theory at very large distances or at very small distances. If you are at critical points of your theory, the CFT can be interesting. Sometimes the CFT are trivial. So what is a trivial conformal? What's a trivial conformal field theory? What's a trivial theory that has scale invariant? A free theory, right? A free scalar, just a free scalar. Propagator is 1 over the distance. So some power depending on the dimension, and that's it. It is definitely power law. I mean, a free scalar is an example of a scale invariant theory. But if you tune, you can go to conformal invariant theories that are not trivial, that are not free. Okay? So let me just give you a few examples of these kind of pictures, very simple examples. So you have seen renormalization, right? You have encountered already this kind of pictures, right? The UV, IR, and flow, and so on. Is it true? Very good. But still, maybe this will be then a bit boring for you, but I'm still going to give a few examples. Okay? So one example is consider a free massive scalar. Okay, so our Lagrangian is just in d dimensions, and then we have a kinetic term plus some mass. Okay? So what happens in the UV? Well, in the UV, if you consider very high energies or very short distances, this mass is irrelevant. You can totally ignore this mass. Then, in the UV, you get a quantum field theory of a single, free, massless scalar. Right? You get just one massless scalar. The mass is irrelevant at very high energies, you can ignore it, and that's what you get. On the other hand, if you go to the infrared, if you go to long distances, right? You go to long distances, your field is massive, so you don't see it, right? The correlations decay exponentially. So you have nothing. You have the empty CFT if you want. So you have nothing. So you have the empty, let's call it the empty CFT. There's no correlation. No field survive. This is what happens, for example, in those cases that we saw these pictures before that you were asking. If we don't tune the temperature, that's where we will end up when we zoom out in these pictures. This is one example. Let's consider another equally trivial example. For example, one massive scalar and one massless scalar. This is okay? So can someone tell me, someone that is thinking live, that did not know this answer before the lecture? What would be the UV? What happens at very high energies? Someone?
2 massless squared.
Yeah, very high energies. We don't care about the mass of this particle. So we have a CFT, which is a CFT here, with 2 massless scalars. What about in the infrared? Only one. At the infrared, the massive guy decouples completely. So we have a CFT with 1 massless scalar. Okay. We can have a standard model. Or, of course, the UV completion of the standard model. What happens in the infrared when we zoom out? Well, we get photons. That's the massless stuff that we have, right? What we have which is massless around us is QED. So we end up with free Maxwell vector field. That is QED. What happens if we start now from something that is not exactly a quantum field theory, but some lattice model? Let me call it lattice 1 to indicate some lattice model. Okay? Then what can happen is you have some spin system, you tune it at the critical temperature, and you can flow to some critical theory at T equal to Tc, and you have some universal behavior of correlation functions, and you have all the usual story of critical exponents, etc. Is it clear? So this is a critical phase, like the ones in the picture. We can get there, or we can go to an empty CFT if we don't tune the temperature. But now you know this thing very well. You know that if we are zooming out, is it really important if our lattice was a square lattice or a triangular lattice or an hexagonal lattice and so on? We expect not, right? We expect that if the interactions are similar, as we zoom out, we wash out the details of the discrete. So we expect that there are, of course, other theories that could very well flow to the same theory in the infrared. So there is an important notion that there are universality classes. That different theories, even quantum field theories, this is true also this is also true for quantum field theories. You can have different quantum field theories that you can also have different UV quantum field theories that flow, that in, as you zoom out, that are the same. That's pretty obvious, right? For example, just add more massive modes to the second example, to that second example, and of course, in the infrared, you always get one massless scalar. So as you zoom out, of course, there are many theories that flow to the same thing. So there is this notion, again, of universality, which is a very important concept in physics. For example, these kind of spins that we are describing, these spin systems of spin up, spin down, interacting with nearest neighbors, and so on. Consider this system, say, in 3 dimensions, where you have the so-called 3D Ising model. It is in the same universality class as the water-liquid 3 critical phase transition. So the transition, the phase transition, the water phase transition, is in the same universality class. That is, correlation functions have the same exponents as, for example, the 3D Ising model. So studying conformal field theories is something extremely important. It teaches us about universal features of quantum field theories. Okay? So any quantum field theory, as we were saying, can be anchored to 2 CFTs, one in the infrared, one in the UV. Okay? Well, not exactly. Sometimes we can define a quantum field theory by a lattice in the UV. Then in the infrared, we flow to a CFT. But we can also consider theories that in the UV can also be described by quantum field theory. So conformal field theories are the endpoints of RG. This is always true. So if you follow the RG, conformal field theories are the endpoints of the normalization group. And furthermore, close to a CFT, there are tools to study theories close to a CFT that are not the usual perturbation theory, but which is called conformal perturbation theory. Where we can expand around the conformal theory. You can imagine that you have some theory which is conformal, say with some Lagrangian, and treat the deformations of that Lagrangian that break conformality as small operators that you expand down and treat as perturbations on your conformal field theory. So if you control very well conformal field theories, you can treat the deformations of that theory as a small perturbation that you compute on the background of the CFT. And there is a huge technology developed for studying exactly this conformal perturbation theory. Finally, a great deal in the recent years has been learned about the properties of RG flows. You might think that everything was known about RG flows since Wilson, but it's not true actually. You might wonder, okay, you have different conformal field theories. So here are some conformal field theories. Here are some other conformal field theories that flow to another infrared, at the inference infrared. What exactly do we know about the spaces of quantum field theories and their infrared and UV fixed points? Is there some kind of foliation? Is there some kind of foliation of quantum field theories? Is it possible to draw some kind of picture like you have a plane, and then you have another plane here? Is there some kind of foliation of conformal field theory, of quantum field theories? Is there some kind of time as you go along the RG flow? And there are quantities, there exist some quantities called C functions, CFT, that are monotonic along RG flows. There are quantities that measure some kind of a time. That if you measure in your quantum field theory what is this function, and you measure it at 2 different energy scales, you know this one can be obtained from this one in the infrared, maybe, but the opposite can never be true. So there are quantities that always increase as you zoom out. They always increase as you move to the infrared. So you can immediately ask, if you have 2 quantum field theories, can I zoom out from this one and eventually end up with this description? Well, unless this quantity is increasing, that can never happen. So there is a great deal of things being understood about this, about the nature of RG flows, really in the past years. For example, the existence of these quantities that foliate the space of quantum field theories was probably understood last year, I think, beyond 2 dimensions. So in 2 dimensions, it was known since some works of Zomological, like 30 years ago. But in 3 and 4 dimensions, this was understood last year or over the last 2 years. What exactly is how exactly to foliate quantum field theories? If you want, this is the main motivation. Right? Conformal field, this is the main motivation for studying conformal field theory. But there are 2 other huge motivations for studying conformal field theory. That even if it was only for those 2, it would definitely already be more than enough motivation to study them. One of them is that conformal field theories define quantum gravity in a box. In a box, that is a gravitational box. There is a space-time called de Sitter that effectively behaves like a box. Okay, what does it mean? It means that you send some particle to the right, and the particle goes, sees some gravitational potential, and comes back. Exactly as if you put it in some kind of box, and it reflects off the wall and comes back. So this is a very nice space-time. It's the analog of our box. So physicists, we like boxes to do experiments inside. ADS is a covariant box. And if you want to ask questions about quantum gravity in a box, this is the way to put gravity in a box. What turns out to happen is that you have this box, which has a boundary, like the boundary of the box. And there is a formal field theory that lives on this boundary that holographically defines quantum gravity in the box. Of course, these words are kind of mysterious right now, but we will develop this further throughout maybe 1 week. So this is the concept of ADS-CFT. And if we want to draw some kind of cartoon, there is some boundary of this space-time. The boundary can be flat space, R-dimensional flat space, or R1, D if you want Minkowski. This is just a question of signature. And you have some conformal field theory in this boundary. And inside, there is an extra dimension, which is called the ADS radial direction. And if you want to consider a correlation function of operators in your conformal field theory, what you do is each operator sources some kind of string. It's like putting a source at the boundary. You have your box and you kick it with a hammer and a string goes. You kick it with another hammer and a string comes out. So you inject 3 strings and you study the string path integral with 3 string insertions. And you sum over the strings that live in this space. So this space here is ADS spacetime, or ADS D+1. It's a D+1 dimensional spacetime. Okay, very good. So, so this would be already a huge motivation for studying conformal field theories, to learn about, which would be to learn about quantum gravity and about string theory. So if you want the best definition, in my opinion, of string theory that we have right now, is by saying that string theory is the dual of a very precise conformal field theory that we will study in a week or so. Probably the third main motivation, outside critical phenomena, RG fixed points, and quantum gravity, is just string theory. String theory is a theory of 2-dimensional conformal field theories. Now, I know that this year, your approach to string theory was not based at all on this picture of conformal field theory. Okay? But you were probably told, I bet Barton probably told you that later you should supplement what you learned by learning that there are conformal field theory methods for studying string theory and so on. Is this a fair statement? Did he mention that? Did he say, okay guys, we used this light cone approach, but there is also a worldsheet, conformal field theory formulation, and so on, which would be very useful if you study it by yourself. Did he end his lectures with this statement? Was this right? No? Okay, but it's a true statement. So what is string theory? What's the definition of string theory? String theory is the following. you have some strings. So let's define string theory by defining some physical quantity. Let's define the S matrix of strings. So suppose we have 3 strings and we scatter them, and we have some pair of pens like this. And then the definition of string theory is the following. You sum over all possible string surfaces, over all possible so-called world sheets. This is one world sheet. This is another world sheet that has one hole. Okay, so it's like a torus with 3 punctures, tack, tack, tack. Plus, you sum other stuff. And this cartoon that we will try to make semi-precise by a formula is what defines what we call the string S matrix. And let's try to write down some kind of equation that describes this cartoon. So what do? We sum over surfaces of a certain genus G. So the genus is the number, is related to the number of holes that the surface has. What's the topology? Then we have some string coupling, G string, to the power 2G plus some integer that depends on the number of external particles. It's not important, it's constant for the full S matrix, so it's irrelevant. So the more handles you have, the more powers of G it costs. So you can think that this string here is moving, and then it pays a G string to split in 2. It pays the power of G string. This one is moving, it pays the power of G string, and these powers of G string appear here. Okay, this is the cost for a string to split, how expensive it is for them to split. And then you make an integral over all surfaces of genus G. So it's a path integral. You sum over all surfaces of genus G that are given by some embedding X that depend on sigma and tau. Right? So we have a map between 2 dimensions. For example, in this case, a sphere with 3 punctures. And we have some sigma and some tau that parameterizes this 2D sphere. And there is a map from the world sheet to the target space by some vector x of sigma and tau. That is a 10-dimensional vector. Right? So each point in this sphere is mapped to a vector in 10 dimensions, so that as you go around the sphere, you draw the picture there in 10 dimensions. And similarly, you have a map from another 2D surface, which is a torus, again with 3 punctures, into this one, plus etc. So these are the maps from a given world sheet of topology G into the 10-dimensional target space. And then there is some action, e to the minus square root of lambda, times some action functional that depends on this vector x. And then if you have, in this case, 3 punctures, there would be 3 operators that you average, v1, v2, v3, that are called vertex operators. Okay? So this is, if you want, the definition of perturbative string theory, which actually, without ADS-CFT, is more or less the only definition we have of string theory. It's by its perturbation and expansion. Okay? This is probably chapter 3 of Polchinski volume 1 or something like that. Okay? So if this is not totally familiar, if you want, you can read a bit more about it in Polchinski. We will actually not use the right-hand side of this formula, except maybe in the 3rd week. We will use the cartoon. This might be a bit surprising. How come we are going to use a cartoon and not a precise formula? But this will become clear in a week. So next week, we will mostly use the cartoon part of this formula. This part serves as an inspiration, because what's really important here is that this action here, this theory, this 2-dimensional theory, this is a 2-dimensional conformal field theory. That's the way string theory is defined. So it's very important to learn how to study 2-dimensional conformal field theory. So this action, you remember in your case study, is the area of the string. This guy here is the tension of the string. So if the tension is very large, then what happens is that the surface almost does not oscillate. It cannot oscillate a lot because quantum fluctuations are very suppressed. Roughly only the minimal area contributes, and you get classical strings. If lambda is of order 1, then your surface can fluctuate a lot. Because fluctuations, the tension, the string is not very tense, so it does not suppress this fluctuation. If G string is very small, then these diagrams are much more important than the diagrams which contain a hole in the middle where the strings can split and join again. So holes become suppressed and fluctuations become suppressed. So the easy regime of string theory is easy for G string going to 0 and lambda going to infinity. That's when string theory is simpler. It is just classical strings that do not split. Classical free strings. It should be said that you might ask, okay, I told you that conformal field theories have more symmetry than quantum field theories. You might ask, how much more symmetry do they have? Right? Do they have much more symmetry? In 2D CFTs, for 2D CFTs, the conformal symmetry is infinite dimensional, which makes it really super powerful. To the extent that we understand really a lot about two-dimensional conformal field theories, because the symmetry algebra, the new symmetry that we get by studying conformal theories is infinite dimensional. It is finite dimensional for higher dimensions, which should be the ones that we'll be studying in this lecture. So there is a beautiful subject of studying conformal field theories in 2 dimensions, where we explore this infinite dimensional algebra, and which I am not going to touch upon, but it's very important that you know that it exists. Okay. So this concludes the basic motivation / overview of what are conformal field theories. And I am more advanced than I thought I would be, which might mean that I'm going a bit too fast. Is it true? Am I going a bit too fast? So please ask me questions about what we have seen so far. Okay? So you see, we zoom in a lot. So let's repeat what we have said. So very high energies, the energies are much bigger than the masses of the particles, so we can ignore the masses. We end up with a conformal field theory. We have massless excitation. The energy is very small. Then if there's something massive, it decouples, so we don't care. So by definition, we end again with a CFT. So CFTs are the endpoints of the renormalization group. Zoom in a lot, zoom out a lot, you get a CFT. Often, the infrared CFT is boring. If everything is massive, you go away, there's nothing remaining when you go to very long distances. Right, that's okay, right? I mean, we zoom in and zoom out a lot, it looks black. We zoom in a lot, we start seeing some electrons moving and so on, and it looks more interesting. So that's okay, that's fair. If we tune the theory, sometimes when we flow, we end up with something interesting. For example, in critical phenomena, we tune the temperature, we zoom out, and we can end up with some non-trivial conformal field theory. For example, you saw in your lectures with John that if you tune 4 minus epsilon dimensions, you can study the criticalizing model. And you compute the dimensions as an expansion in epsilon, where epsilon was the deviation from 4 dimensions. Do you remember this? Yes? Is it familiar? You study this Wilson-Fischer fixed point in 4 minus epsilon dimensions, and you study this critical phenomena that appears in this 4 minus epsilon dimension. And then John told you that you could decrease this epsilon all the way to 1 or even to 2. Right? If you did it to 1, it's a crazy expansion. You expand in small 4 minus epsilon. So epsilon is small. It's close to 4 dimensions. But you trust your gut. You go all the way to epsilon equal 1 to 3 dimensions. Then you should be describing the 3D Ising model. And indeed, you are computing the critical exponents of the 3D Ising model or of boiling water. And then you can measure and check that it does work. Okay. That's about statistical physics. We saw that there is this notion of universality, of course. We can have different theories that differ by details that at very long distances are irrelevant. So therefore, there is this notion of universality, that different theories can zoom out to the same theory. And there's even recent progress in understanding very well the space of RG flows and how exactly the quantum field theory is organized from this RG flow point of view. Conformal field theories, from a completely different point of view, describe quantum gravity. They define quantum gravity. If I don't know how to define what is inside. It's like a crystal ball. I know what are the rules of the game in the boundary. It's the quantum field theory. I compute. I see what I get inside. And this defines whatever quantum gravity is. Very powerful way. And string theory, it's the sum of maps in 2 dimensions given by a conformal field theory. So conformal field theories are theories, again, let me emphasize again, with more symmetry. In particular, very important, they have what's called local scale invariant. So conformal field theories, yes?
Regarding that formula there, so what is the relevance of the F matrix? Are we interested in the scattering of strings? Or what?
Yes.
And how does... Okay, so,
That's right. So what are on-shell observables? What can you measure? I mean, what can you measure in a quantum field theory? You measure scattering of stuff. By measuring how things scatter, you can measure the masses of the resonances. The spectrum is contained is information that can be read off from the S matrix, right? You just scatter and see what is flowing in your S matrix. You see what are the resonances and you measure the spectrum. So string theory, there is no off-shell definition of string theory. There is no way where you can study things that are, the only observables that we know how to define in perturbative string theory are on-shell processes, where you scatter on-shell particles, which are on-shell strings, and see what is their amplitude for a given scattering process.
So is the scattering of strings also relevant for the experiments we do with is the scattering of strings equally relevant to the scattering of particles in the normal field?
It's the same thing.
Okay, so we can
The S matrix we compute from quantum field theory is the same as this kind of S matrix. So that brings me to an important comment that I actually forgot to say. Good that you asked. Very good. So indeed, there is a limit of string theory, where string theory... No. Can I ever get that one? No? It's front rear fixed, right? No. Okay, I understood the logic. From now on, I will never fail. Very good. So indeed, there is a limit where the tension of the string is so huge that the string wants to shrink to a point. And then this diagram, at large tension, what happens is that then you recover field theory. That is, if you look at very, very far away, these tubes, they look like a single particle. So what is this diagram describing here where you have a hole? This diagram is describing something where you can have a Feynman diagram which contains a loop. Now, the beauty of string theory is that this guy here, as the tension goes to infinity, does not contain only this guy. It contains also other diagrams that you can imagine. Say, something like this, plus, let me try to draw a different one. What can it be? For example, something like this. All one-loop diagrams, all diagrams that, if you imagine thickening the diagram, they would have this topology. They are all automatically contained by the fact that you sum over the surfaces. That you fix the topology and sum over all surfaces of this topology. So one of the beauty of string theory is that all these diagrams that appear in quantum field theory, they are all automatically captured by a single string diagram. It is just, you can imagine that there are surfaces. Imagine that these lines are small tubes. By summing over surfaces, there are surfaces that look like this, like this, like this, like whatever. So just by summing over the shape of surfaces of a given topology, automatically you capture all possible diagrams with a single loop. All possible diagrams at tree level and so on. So it's a very powerful idea in string theory that is very well described in Green, Schwarzschild, and chapter 1, which is a beautiful, beautiful chapter. I recommend everyone to read it. Also, what are the dangerous points in quantum field theory? The dangerous points, so let me first stress out what I just said. These diagrams are all contained in this diagram. So, What are the dangerous points? The dangerous points in quantum field theory is when, say, this interaction point becomes very close to this interaction point and so on, or you start getting divergences. But there's no such notion in string theory. Once you start talking about smooth curves, all that is smoothened out. There's no point where the string splits. There is no Lorentz invariant way of specifying a point where the string splits. There is no longer this notion of dangerous points in space-time. And this is related to the fact that string theory is UV finite. So it takes away all UV divergences of field theory, and it takes care of all the diagrams at the same time. Okay, very good. So, where am I? I lost my page. I was walking with some page. Did you see where I put? Ah, very good. Okay. Okay. So now let me show you how I don't fail. So tack. Huh? Very good. Ah, no. Huh. Ah, okay. It's possible to do even better. Okay. So they are the natural generalization after theories that have Poincare symmetry. But first, sorry, I was interrupted when I was discussing this point. So conformal field theories are theories that have scale invariance, but more than that, they have what's called local scale invariance. That is, you can imagine a theory which is invariant. Imagine you have a piece of magnet, like the one in the pictures I gave you. Indeed, if you zoom in a part of the material, if you zoom in the full material, you don't see in which scale you are. It's scale invariant. But you could imagine doing something a bit different. You could imagine that you have, say, a big chunk of material here. And in this part of the material, you deform it by a factor of 2. And this part of the material, you deform it by a factor of 3. That is, you see, you apply some kind of dilatations, but different dilatations in different regions of your material. This would be like a local dilatation. You look for theories that are invariant under a rescaling that is local. You can rescale anywhere in your material. Maybe you could say it's not that surprising. If you have a big material, if the fields are not very slowly changing, who would notice if I'm changing? If I'm cheating and changing for a little bit more every time I go to the right until here I'm changing a lot. So this notion of local scale invariance, which is a symmetry that rescales the metric, it rescales your metric at a given point by some factor omega that depends on that point. So conformal field theories are theories that are invariant under this Weyl transformation, as we will define rigorously in the next lecture. Okay. So now I can so then you might say, okay, let's try to motivate conformal field theories from the last point of view, which is that suppose now we forget about more or less everything we said and just want to think from the point of a very pragmatic point of view. Okay, quantum field theories are kind of hard. Okay, if they are Poincare invariant, it's a bit simpler. I have more constraints, right? Relativistic invariance helps. What can I do to put more symmetry on top of Poincare to help me more? Right? If you have more symmetry, this can be helpful. So can I start, instead of having just boosts and rotations, can I start adding more symmetry to my theory and getting some other kind of theories that have more symmetries compared to Poincare that might be simpler to study, and maybe I can first study those and learn about those. So one question we might ask is, how can we start generalizing theories after Poincare? And if we try to do it, this leads naturally to the notion of several alternatives that arise if you try to do it. You get to conformal field theories. Another kind of idea that could emerge from thinking along those lines is supersymmetry. These symmetries that are fermionic symmetries, not bosonic symmetries like Poincare. And yet another idea that could emerge out of these considerations would be two-dimensional, not conformal theories, but so-called integrable theories. So there is a beautiful story about, if you try to think very naively about what can you do to start adding more symmetry, you are led to see that there are four possibilities actually. The main thing that typically happens if you start doing it, so it's a thicker arrow, is that you end up in a bad situation. That is, you end up seeing that if you add more symmetry, the theory becomes free. So you try to add some more symmetry to simplify your life, but you oversimplify. You see that, okay, I try to add a bit more, poof, the theory is free. It's totally boring. So you need to be careful. You cannot add too much symmetry. If you add too much symmetry, everything becomes trivial. And the way to evade ending up with a free theory naturally leads to these three different classes of important theories that are very important in theoretical physics. Conformal field theories, supersymmetry, and two-dimensional exactly solvable models. I think maybe that's a great point to start tomorrow, when we will arrive at this conclusion and start our systematic study of conformal field theories. Okay, so today we end on time. I gain a few minutes, but I'm going to use next lecture.